Good evening, everyone. It's 7:30, and we're going to start on the dot. And I'd like to welcome all of you here in the room, and as well some more people who are watching online to the BRLSI's science group. My name's Stuart Reynolds, and I'm the convener. So tonight, as it says up there, we've got a talk about quantum physics. And before I introduce our speaker tonight, I'll just comment that this is, in fact, the first of two more or less linked talks that we're going to have here at the BRLSI Science Group. Tonight's talk is about quantum light physics, and it's by Alex Davis, who's I'm about to introduce. And in 4 weeks' time, we'll have another quantum physics talk, but this time about quantum materials. And that's going to be given by Alex's colleague, also in the Department of Physics at the University of Bath, Dr. Habib Rostami. And that's going to be equally great. So I'll look forward to seeing you all here again in a month's time for a bit more quantum weirdness. So I better introduce Alex. Alex Davis studied natural sciences at Cambridge, and he graduated with a degree specializing in physics in 2014. And he then migrated to the other place in Oxford, where he did research on atomic and laser physics. And he gained his PhD degree there in 2018. And after that, he did some postdoctoral work at the Sorbonne in Paris. And eventually, he realized that where he really wanted to be is right here. And he came to work at the University of Bath, where he is the holder of an EPSRC Quantum Technology Career Development Fellowship. And he's going to tell you all about that. So,
yeah, thank you very much for the introduction, Stuart, and thank you all for welcoming me here to the BRLSI. Yeah, it's a real privilege to have the opportunity to speak here. So, yeah, I'm going to talk about quantum mechanics, light, and the future of technology. So, quite an ambitious scope for this talk. So, I might be going quite fast, but I'm sure we will be able to keep up. So, the just to explain the image, I think because of Schrödinger, the cat has kind of become the totemic animal for quantum physics in general. So the image of a cat playing with a laser pointer has kind of been co-opted by the quantum optics community as our mascot in a sense. And this is our cat Evie, who is currently in a superposition between having fleas and not having fleas. So the talk is going to be divided into two parts. So firstly, I'm going to be talking about the foundational stuff, the basic nitty-gritty of quantum mechanics, what it is. And to be honest, my main goal in this half of the talk is to basically address some very common misconceptions that many people have about quantum theory. And then I was told that this audience is often quite interested in applications, technology, experimental methods. So for those people, the second half of the talk is about the current drive towards quantum technologies, which I and many other people across the world are now working on. And I'm going to introduce some of them, including quantum computers and quantum cryptography. And I'm going to just start to touch on the work that we're doing on realizing these technologies using photonics, so light. But before I get stuck into it, I just want to make a sort of general statement about quantum theory and how it's understood by people. So there's almost no popular engagement about quantum mechanics that doesn't somehow reference this quote. Nobody understands quantum mechanics. And this is attributed to this guy, Richard Feynman, who won the Nobel Prize for work that he did in quantum mechanics just after World War II. He was also involved in the Manhattan Project. And he made this comment, and I think it's one of the most commonly misquoted or misinterpreted comments in the whole of physics. The first reason I think that is because it's something that people often say when they themselves have given up trying to understand quantum mechanics. So it's not very helpful from that perspective, because people think, well, if even the guy who won the Nobel Prize for doing it says that nobody can understand it, then I don't understand it, so I might as well give up now. That's not very helpful. The second reason that I think it's often misinterpreted is because it often goes hand in hand with words like this that are used to describe quantum mechanics. Counterintuitive, bizarre, mysterious, paradoxical, nonsensical, spooky. The reason people use these sorts of words is because they've discovered from experience that you can drive more engagement with people if you cloak your subjects in a shroud of esotericism and mystery. And we're all guilty of that. It's not just crackpots trying to sell you healing crystals and convince you they're telepathic that are using these words. Physicists do it as well. I even did it to some extent in the abstract for this talk. But it's maybe not such a helpful thing, because it implies that quantum mechanics is like some kind of black magic, and that we don't really know what we're doing. All we're doing when we're doing quantum mechanics is like consulting a sphinx or something, and it answers in riddles, and nothing really makes sense. It's all like a big spell book. That's not true at all. Quantum mechanics is very precise physics. It's physics as much as Newton's laws of motion or anything else you might have studied in school. It makes precise predictions. It's completely consistent. It's verified experimentally. Quantum theories are the most successful scientific theories that have ever been developed and demonstrated in terms of how they describe the real world. So what did Feynman actually mean when he said nobody understands quantum mechanics? Well, a few sentences later in the lecture where he gave this quote, he provides some very useful context. He says, but the difficulty really is psychological and exists in the perpetual torment that results from saying to yourself, but how can it be like that? Which is a reflection of uncontrolled but utterly vain desire to see it in terms of something familiar. And what Feynman is really talking about is what we think we mean when we say we understand something. Because a lot of people, when we study fluid mechanics, for example, you build a mental picture of molecules moving around like billiard balls, and you draw reference back to principles that are familiar to you and grounded in your understanding of the world. But quantum mechanics is more fundamental than that. It goes to a deeper level of reality, and it forces us to discard a number of sort of comfortable home truths that we always resort to when we try and understand something. So the reason nobody understands quantum mechanics is not because it's impossible for humans to understand it. It's because we don't really know what we mean when we think we understand something. But in the sense of being able to make precise predictions and to characterize the world and provide us insight into how the world works, quantum mechanics is as solid as anything else in the whole of science. So I'll get into the talk now. What is quantum mechanics? So quantum mechanics made such a dramatic change to physics, such a deep departure from the rest of physics, that we classify all of physics into quantum physics and what we call classical physics, which, broadly speaking, historically is kind of what came before the discovery of quantum mechanics. If you didn't study physics past school, then everything you'd have done is classical physics, Newton's laws of motion, etc. So here's a classic example of a problem you might have encountered in classical physics. A guy tosses a ball and the ball flies for a bit and lands. We can use this this example to see certain characteristics that are common across all of classical physics. So there are certain broad principles that underlie everything in classical physics, and we're going to see that that quantum mechanics departs from these. So the first is this idea of locality. So locality is the idea that basically we can describe the universe completely. We can decompose the universe entirely into bits of matter and energy that is described specifically at a specific point in space and time. And when changes take place in the universe, they propagate continuously through space and time. So the guy throws the ball, and the ball flies through the air and lands. And at some point, the ball occupies every point in this arc. There's nothing in classical physics where I can do something over here and it will instantly affect something over there. You know, you can send a radio wave or make a sound or something, but all of those things propagate through the medium between the source and the receiver, right? So classical physics is entirely local. Another thing is determinism. So when you're given your A-level physics problem, you're told how hard the guy throws the ball, and maybe if it's like a university, mechanics problem, you might also be told the air resistance and the mass of the ball. But in principle, if you know everything about the initial conditions of this system, then where the ball lands and everything else about this problem is completely determined with absolute certainty. The laws of physics are like clockwork. If you know the initial conditions, then you can determine how the system will evolve for the rest of time with absolute certainty. There's nothing probabilistic about it. As Einstein said, in classical physics, God does not play dice with the universe. There's no element of intrinsic randomness in classical physics. And the last sort of deep underlying feature about classical physics is what I've called observer independence. So this is the idea that stuff happens and you can make measurements on stuff, you can observe stuff happening, but in principle, your decision to investigate a system does not affect how the system evolves, right? If a tree falls in the woods, it doesn't matter whether there is someone there to hear it or not, the tree still falls in the woods. And in classical physics, the outcome is the same. If someone then comes into the woods later and has a look at the tree, then it doesn't matter whether anyone was around there. So in principle, measurements can be non-invasive. Yeah. So in terms of the history of classical physics, basically Newtonian dynamics. So this is things like the motion of objects like the throwing of the ball, or like springs and clockwork, and also fluid mechanics. Basically all mechanical stuff, dynamics of objects. So the rules underlying this were laid down by Newton in 1687. And Newton also came up with a theory of gravity at that time. But actually, Newton's theory of gravity does not obey the principle of locality, because in Newton's theory of gravity, the sun, the moon, and the earth are all interacting with each other instantaneously. If in Newton's view of the universe, if the sun just disappeared, then the earth would immediately start flying out of its orbit, and the earth would feel the effect of the sun's disappearance instantaneously. So actually, Newtonian gravity is not local, but that gets redressed. So later in 1873, this guy, James Clerk Maxwell, came up with a theory of electromagnetism, which basically completely describes light in a classical way, and also electricity and magnetism all unified together in a very nice framework. And in this framework, light is a wave, an electromagnetic wave. So Maxwell's formulation for electromagnetism actually created some tension with this fact that that gravity is non-local in Newtonian dynamics. So for a while after this, and with some subsequent experimental results as well, this tension mounted, and it was resolved in 1916 when Einstein invented general relativity. General relativity is classical physics for the purposes of this talk, this provided a more general theory of gravity, which actually restored locality, and also predicted the existence of black holes and a bunch of other stuff, which I'm not going to touch on too much in this talk. So together, these things basically are the main pillars of classical physics, and they have all of these concepts built into them. And I put it to you that it's our internalization of these ideas that makes quantum mechanics, which I'm about to go into, difficult for people to believe they understand. So classical physics is a beautiful, self-consistent edifice, and it describes many things wonderfully. So when NASA launched their their space probes around the solar system. They use classical physics, and it predicted things very well. In fact, until 1900, there was basically there was no experimental reason really to believe that there was anything wrong with classical physics. But around that time, a number of experimental results came in that revealed that classical physics actually did not really describe the world that we live in. So there are several pieces to the puzzle. The first one was something called the photoelectric effect. So this is the observation that when you illuminate some material like a sheet of metal with light, then sometimes an electron will fly off. But this only works for certain colors bluer than a certain threshold. And if you illuminate the metal with light that's redder than a certain threshold, then no electrons come out. And it doesn't matter how bright this light is, it's the color that matters. And classical physics had real trouble explaining this observation. Another problem was something that's come to be called the ultraviolet catastrophe. Catastrophe tells you how bad the implications are of this for classical physics. So basically, this is if you heat something so that it starts glowing, for example, like a heating element in a stove, and then you look at the spectrum of colors that come out of this thing. So here, this is basically a spectrum with blue light over here and red light over here. So classical physics makes a prediction about what the spectrum of light should look like from this glowing thing. And it predicts that you should just get more and more blue light. The shorter the wavelength you look at, the brighter this thing should glow. And in fact, the prediction is quite problematic because it actually predicts that this goes up to infinity and it should emit an infinite amount of energy at very, very short wavelengths. So that was very, very bad. And it also conflicted with experimental observations because actually you can see that these curves correspond to different temperatures that things are glowing, but you can see that the intensity always goes back down again to zero at very short wavelengths. So in 1900 and 1905, Max Planck and Einstein thought about this, and they basically came up with an idea of how to resolve this, which is that these results could be explained if light isn't actually entirely a wave, if it actually consists of particles, and its interaction with matter is because particles are being absorbed. And the reason that the photoelectric effect happens is because particles of light over towards this end of the spectrum have more energy than the ones over at this end of the spectrum. So the ones over on this side of a certain threshold have enough energy to kick an electron out of the medium, whereas these ones don't, so nothing happens. And this also explains the photoelectric effects. And this is the origin of the name quantum mechanics. So quantum is Latin for amount, with the implication of being like a discrete amount, like a grain of something. So the idea that light is actually comprised of these quanta is where the name comes from. There are other clues as well. So around the same time, people did some experiments that devised the structure of the atom, and they discovered that the atom consists of electrons orbiting an oppositely charged nucleus. And classical physics makes a prediction as well about what kind of what should happen in this situation. And it predicts that the electron should just emit radiation at all wavelengths and spiral in towards the nucleus, towards its doom. But in fact, atoms are stable, which is fortunate for us because we're made of them. And when you do look at what light atoms emit, and you can get them to emit by exciting them, by heating them up, for example, in a flame, they only emit at certain very specific wavelengths. And so this also couldn't really be explained by quantum theory. And the last big piece of experimental evidence, which I'm about to talk about in more detail, is the double slit experiment. So what is the double slit experiment? Well, I think hopefully most people here will remember those old cathode ray tube TVs. And what they are is basically an electron gun. So this is basically just something that emits electrons, and it fires them through the vacuum onto a screen. And this screen has a material on it which just gives a little spot where an electron hits it. So you build up basically a sort of pattern like this, where all the electrons hit the screen. And what you can do is you can put a mask in front, which will basically block, will let through some of the electrons where there's a hole in the mask, but block the ones where there's no hole. And then, unsurprisingly, you find that you get more electrons sort of behind the hole than behind the mask. And this happens as well, obviously, if you change the position of the hole. So the question is, what do you observe if you have two holes? And given that these electrons are going through one by one, okay, you can turn down the intensity of the electron gun so that you only have one electron in flight at any given time. You might expect the pattern that you would see to be just the sum of these two distributions. After all, if each electron is either going through one hole or the other, then what you get should just be, you know, the compilation of the two. But that's actually not what you see when you do this experiment. Instead, the pattern you get looks like this. And you can see that you get electrons behind the mask at points where in the classical expectation there would be very few electrons. That's actually where you get the most. And you get this sort of alternating pattern of bright and dark spots where you get more electrons and fewer electrons. So why does this happen? Well, physicists were familiar with this kind of pattern already. They'd seen it before. And they'd seen it before because it's characteristic of how waves behave. So if you imagine that this is like a ripple tank and you send waves of water through, then the ripples sort of head out and they constructively interfere. And in the lines where the crests of the waves line up, that's where you seem to get more electrons, and you get fewer where they interfere destructively. But the thing is that electrons are particles. So what does this wave correspond to? Well, the wave seems to determine basically the probability of finding an electron. So at the points where you get constructive interference, that's where you're more likely to find an electron. You don't know exactly where an electron is going to appear, whether it's going to appear in which fringe or wherever, but this wave seems to give you a helpful piece of information about where you expect to find them. But the thing is that this pattern is characteristic of the wave propagating through both slits. But surely if the electron is a particle, it can only go through one slit. So another complication, interesting observation is what happens when you try and check which one of these slits the electron goes through. So you can put a detector here, which will basically just measure whether the electron goes through, and one on the other slit as well. And it will give you a click and let the electron through if it detects it. And you do this and you always find only one detector clicks. It will always tell you the electron has only gone through one slit or the other. But then if you condition on the events where this detector clicks and the electron has gone through this slit, then you find the classical distribution of where the electrons are, and similarly on the other one as well. Now, here's the interesting thing. If you forget what the outcomes of these measurements are, or you just don't bother writing them down or don't pay attention to them, then the distribution is not the interference pattern. It's just the classical particle-like distribution. So the mere fact that something has happened here which could, in principle, have measured which path the electrons go through seems to change the distribution of where the electrons end up. So the idea of measurement plays a really important role in actually changing the dynamics of the system. So we call this behavior wave-particle duality. And basically, these are the assertions of it. Fundamental particles, so I've talked about electrons here, but photons, which are these quanta of light, also behave in the same way. But they behave as particles when they're measured. When you measure them, they always seem to be, if you measure their position, then they always seem to be in a particular place. But between measurements, their behavior is more like a wave. They propagate out in this probabilistic way, and in a way that can give rise to these interferences. And the wave determines the probability of a particle having a particular property. And another important thing that we need to touch on is the uncertainty principle. So you can have a hole in your mask and you can put a lens in there, which will focus the electrons down to a particular point. So now all the electrons are hitting a relatively small spot on the screen. But if you were to try and measure where the electron was passing through the slit, now you've got quite a big aperture. So there's a very wide distribution in where the electrons can pass through the aperture. So you can think, okay, what happens if I try and shrink this down? But because where the electrons end up is determined by this wave-like propagation, the spread here is determined by the properties of waves. And waves do this thing called diffraction, which is when you try and force a wave to go through a smaller and smaller slit, it spreads out more afterwards. So when you try and reduce the size of the aperture, yeah, you reduce the spread at which the electrons could be passing through the mask plane, but that has the effects that it increases the distribution at the image plane. And yeah, you can squish them right down to a point, and then you find the electrons can be anywhere by the time they get to the image plane. So what we say is that these two measurements, one measurement of where the electron passed through the plane of the mask, and one where the electron hits the screen, we say they're conjugate. So these are two different measurements, and we call them conjugate, and they cannot be known simultaneously, because the more you try to sort of pin down and determine how precisely one of these parameters is, the broader the distribution is in the other parameter. So you can't know everything about the electron. You can't know where it passed through the mask plane and the image plane. You can kind of choose which piece of information you have, but the more precise one measurement is, the more blurry the other one gets. So these are the basic ideas of quantum mechanics. Outcomes of measurements are probabilistic. These probabilities are determined by the interference of the wave function, and measurements, or any interaction that could even in principle be used to make a measurement, can change the state of the system. I've underlined this because one of the big misconceptions about quantum mechanics is that you have to have a conscious observer actually taking notes about the measurement. That you don't have to have that. You just have to have any interaction which could in principle be used to make the measurement. No one actually has to record the outcome of the measurement. So yeah, any interaction with the environment, for example, that determines which slit the electron or photon pass through, kind of constitutes a measurement for this purpose. And these change the state of the particle. Another important concept that I'm just going to run over is quantum superposition. So this is just terminology. When the wave function contains multiple components in a particular basis, we call it a superposition. So here we have an electron. This interference pattern corresponds to the electron passing through sort of both slits, and this is a superposition of the electron passing through this slit and spreading out in this way, and the electron passing through this slit and spreading out in this way. And this idea of superposition doesn't just have to apply to particle trajectories. So in the example of the double slit experiment, we're talking about the position of a particle where it passes through a particular plane. But in fact, superpositions can apply to any physical degree of freedom for any particle. So for light, light is an electromagnetic wave, and it has this property called polarization, because it's a transverse wave in 3 dimensions. Basically, if it's going this way, it can wiggle like this, or it can wiggle like this. And we call this way horizontal polarization, and this way vertical polarization. And this is just one of many degrees of freedom of light. There's also the color of the light is another degree of freedom. And you can have superpositions of these things. So we represent horizontal polarization like this and vertical polarization like this. But just in the same way that you could choose to measure the electron in the image plane, or in the lens plane, or the image plane, you can do a conjugate measurement of polarization as well. So you can also imagine a basis in which your electron is wiggling like this, which we'll call the diagonal basis, or like this, which we'll call the anti-diagonal basis. And this is a conjugate measurement. And if you prepare a photon in the horizontal basis, and then you do a measurement in the diagonal anti-diagonal basis, then because of the uncertainty principle, you get these two equal probability of these two different outcomes, right? And similarly to this one. But we can construct a superposition of these two. And in fact, there's two different superpositions. And then when we measure these states in the horizontal and vertical basis, because these are superpositions, we can get either horizontal or vertical with 50% probability. But when we then measure them in the diagonal anti-diagonal basis, we get constructive, for this state, we get constructive interference for the diagonal polarization, and destructive interference for the anti-diagonal polarization. So we have 100% probability then of measuring diagonal polarization, whereas with this one, we have 100% probability of measuring anti-diagonal polarization, which is a bit weird if you think about it, because previously, this state we think is a superposition of each of these two. And when we measured either of these in the diagonal, anti-diagonal basis, there was some probability of getting the anti-diagonal. But the superposition of the two, because you get this interference effect, the probability of measuring the anti-diagonal disappears for this one. So this is also kind of this is how superpositions work and how wave dynamics can work in a smaller degree of freedom with only two possibilities. So firstly, let's go back to our classical principles. We can see that determinism is completely out the window. Physical properties are decided randomly. God does play dice with the universe. We don't know where the electron is going to end up. When we perform the measurement on the electron, it could appear anywhere on our screen. When we perform the measurement on our polarized photon, depending on what basis we perform it in, it could be horizontally or vertically polarized or something else. So predicting events with certainty is no longer possible. We don't live in a clockwork universe. You can know absolutely everything there is to know about the state of the universe, and you can't predict the dynamics of it any further. And the uncertainty principle also says that for a particular particle, we can't know everything about it at the same time. Also, the principle of observer independence is out the window as well, because the choice of whether and how to measure affects the particle. And events are not independent of who is watching them and how you're watching them. If you choose to intervene by making a measurement, then you do actually change the state of the system. So I've been talking about fundamental particles like photons and electrons so far, but back in the 30s, Schrödinger proposed a thought experiment, which is like, well, fundamental particles behave in this really weird counterintuitive way that defy these principles that all of our other theories are based on. Why do classical things like stars and planets and cats seem to behave according to these classical principles? So why does big stuff look classical? And it's not to do with the fundamentality of particles, because in fact people have done double slit experiments with atoms. And atoms are not fundamental particles, they're composite particles. They consist of many electrons and protons and neutrons. And every few years, someone basically does a double slit experiment with a bigger and bigger molecule. This, I think, is the record at the moment from 2019. And this is a massive molecule. This is hundreds of atoms in it. And people have observed that even this displays this quantum mechanical behavior. So the question is, how big does something have to get before it starts behaving classical? So Schrödinger phrased it as saying, can a cat be in a superposition of both alive and dead at the same time? We don't observe that, so why not? And this is kind of a very deeply discussed question. It's this is actually probably somewhat a matter of opinion what I'm going to say now. But the idea is that basically anyone who's owned a cat will know that cats are very, very difficult to completely isolate from their environment, right? And because of that, this is kind of the important concept that we go back to this slide. When you measure which slit the electron goes through, then you revert back to the classical pattern. The quantum effect, the interference seems to disappear. So basically, any process that effectively measures which slit the cat will go through, basically then projects the cat into a particular state where it says it's gone through this. And then after that, the cat will revert into its wave-like behavior if we assume that a cat is a quantum mechanical object, and will then spread out a bit more. But very shortly afterwards, because cats are hard to isolate from their environment, something else comes along and effectively measures it. This could be anything. It could be just the air interacting with it, radiation floating around. But something measures the cat and determines that the cat passed through this door, or the cat is alive, or whatever. This instantly projects the cat back into this state. And this keeps happening. And because cats are big, complicated, macroscopic objects, things are interacting with them all the time. So they're effectively being measured constantly. So we don't have a chance to observe this wave-like behavior, because between effective measurements, the cat just doesn't propagate into a different state. So there's no chance to observe these interference effects. So there's a lesson in this, which is that quantum effects are very, very fragile to environmental influence. The reason we don't observe quantum mechanical effects with big particles, big objects, is because basically anything that touches them effectively measures them and collapses the wave function into a particular state. And this is going to prove a very important consideration in the development of quantum technology, which I'll talk about in a bit. Yeah, so now I'm going to talk about quantum entanglement. So we've introduced these ideas of superpositions. So we can have a particle, like a photon, that can be in a superposition of two states, horizontal and vertical. But we can also consider systems of two particles, and we can actually construct superpositions of correlated states. So here we have a state where both particles are horizontally polarized, and here they're both vertically polarized. And we can have a superposition of both of these together. But the important thing is that whichever sort of branch of the superposition we're in, the photons are in the same polarization. So if we perform a measurement on this one, for example, then we project into this state. So we measure the photons being horizontally polarized. And that basically collapses the wave function, gets rid of this part, and we instantly know straight away that the other photon is going to be horizontally polarized. So it seems that measurements on one object seem to have implications for the state of an object that might be very distant. And the thing is, there's nothing to say that these particles have to be next to each other. They could be, one of them could be on Earth and the other one on Mars. And this effect seems to take place instantaneously. So measurements on one object seem to influence the state of the other. And yeah, this should set alarm bells ringing for the principle of locality, which was familiar from classical physics. So people ask, well, maybe we're just being ignorant, because quantum mechanics is a probabilistic theory, and we have a probabilistic theory for a roulette wheel, right? There's a 1 in 36 or whatever, 1 in 37 chance because of the zero that the ball will land in any hole, right? That's a probabilistic theory for how a roulette wheel behaves. But actually, if you knew exactly how fast the wheel was spinning, and you knew exactly how hard the ball was thrown in and the mass of the ball, using classical physics, you could predict exactly where the ball will land. This is a deterministic system. So the question is, well, maybe you could do the same with quantum mechanics. Just like with a roulette wheel, there's parameters that we don't initially take into account, like how hard the wheel is spun, how hard we throw the ball. There might be parameters or factors or variables in quantum mechanics that are hidden, and it's these hidden variables that determine which outcome a particular measurement will give. So actually, the measurement outcomes might not be random. There might be some underlying process that we're just ignorant of that determines what outcome happens. And initially, this was Einstein's opinion, actually. So he said quantum mechanics is not complete. There might be a fuller theory possible, which describes the whole of physical reality and eliminates this probabilistic description. So he had this concept of local hidden variables. Basically, you can imagine a situation like this, where you have two gloves, a left-handed glove and a right-handed glove, and you put them both in identical boxes, and you then jumble those boxes around and send them to two different locations. So now you've mixed them up. You don't know which box contains which glove, but when you open one box and find that it contains one glove, you instantaneously know that the other box contains the other glove. So is this actionless at distance? Because before you open this box, your knowledge about the state of this box is that there's a 50-50 chance it could contain either glove. But then as soon as you've opened this box, you know with a 100% probability that it contains the other glove. So is this action at a distance, even though this is entirely classical? Well, no, clearly not. There's just a hidden variable, which is which glove is in which box, basically. So yeah, this is what we call hidden variables. So are all measurement outcomes in quantum mechanics actually just predetermined? Now I'm going to go over this quite quickly, but the idea is this was actually falsified by a mathematical theorem proved in 1966 by a Northern Irish physicist, John Bell. Basically, there's a thought experiment that we have two friends, Alice and Bob, we have a number of entangled pairs, and we which have entangled with this state, and we give one particle from each pair to Alice and the other particle to Bob. And we can perform, each of them can perform measurements on their state. Now, because this is the maximally correlated state, when they measure in this basis, their measurement outcomes always agree 100% of the time. But the thing is that Bob can choose to measure in a slightly different basis. He can skew his polarization basis slightly. And what this does is it introduces the occasional bit flip. So some of the time, actually, Bob's measurement will no longer agree with Alice's measurement. And equally, Alice can do the same when Bob measures in the original basis and Alice measures on a slightly different basis. Now maybe we get on different events they disagree with. So basically, we end up with something called a Bell inequality, which is that if all of Alice's measurement outcomes for this basis are predetermined and for this basis are predetermined and same for Bob, basically these two lists have to be the same. These two lists of predetermined outcomes have to be the same because we observe that 100% of the time they agree. And this list and this list of predetermined outcomes might have a 90% overlap. And similarly with these two, they might have a 90% overlap. And what you find is that this implies that we have this list and this list of predetermined outcomes have to agree at least 80% of the time, because this one and this one only differ by 10%. This one is the same as this one, and this one and this one only differ by 10%. So there's only so many ways that they can disagree. And in fact, this one and this one have to agree at least 80% of the time. But when you do the experiment quantum mechanically, you actually find that they only agree 60% of the time. And this description defies the idea that you can explain these measurement outcomes by predetermined variables. There's no gloves and boxes to explain quantum mechanics. In fact, you get these weird correlations that can only be explained if there's some way in which the measurement outcomes for one party are influenced by the choice of measurement for the other party. So this is kind of the essence of Bell's theorem. The outcome of Alice and Bob's measurements cannot be independent of the other's choice of measurement. So yeah, and this was then demonstrated experimentally by this guy Alan Aspère with a remarkable moustache with this experiment, and yeah, proved that Bell's theorem holds and describes our world, which is quite remarkable because it means that locality doesn't seem to work in quantum mechanics. And he subsequently won the Nobel Prize for this in 2022, so 40 years after the experiment. But these days, that's how long you have to wait for a Nobel Prize. So yeah, locality seems to go out the window. Outcomes of measurements and isolated systems are related in a way that cannot be predetermined. And the relationship between measurement outcomes seems to depend on the measurement choices of both observers. But the thing is that entanglement is not as simple as saying that Bob can choose to do something to his particle and it will affect Alice's particle in a way she can measure. It's much more subtle than that. So there's something called the no communication theorem, which basically says, the contradiction of that, which is that Bob's choice of measurement on his particle don't provide any information to Alice. It's impossible for Bob to send a message to Alice by choosing a certain choice of measurement, because if Alice can't communicate with Bob, then she doesn't have access to the results of Bob's measurements. And then the measurements on her own particles just seem completely random. It's just random, it's just white noise. There's no information encoded in this. So although Bell's theorem implies that Bob's decisions do sort of influence these measurement outcomes, that influence is sort of buried in the randomness of Alice's measurements. So they can't communicate. The non-locality only becomes apparent when you consider the correlations between their measurement outcomes. And there's one final point that I'll make about entanglement before going into the second part of the talk, which is that the complexity of entangled systems scales very, very rapidly with the number of particles you have. So here we have one particle and it can be in two possible states. Here we have two particles, and there's four possible basis states that it can be in. And this system here can be described by any superposition of these four possible states. If we add a third particle, that goes up to 8. If we were to add a fourth, it would go up to 16, and so on and so forth. So you get this explosion in the complexity of your system with the number of particles involved. So to describe even a medium-sized quantum system requires a huge amount of information. So that, as it turns out, is a good note to move on to the second part of the talk. So this is about quantum technologies and quantum photonics. And it's very relevant right now. The foundations, which I've just gone over, won the Nobel Prize 2 years ago. So that's being actively discussed. And I'm going to talk a bit about the applications of quantum technologies, basically technologies that seek to take advantage of these effects to give us something useful. And you can see that the UK has invested a huge amount of money into various quantum technologies, 2.5 billion just into quantum computing. And the UK is not alone. Other countries are doing this as well. So this is a very hot topic with a lot of funding and a lot of interest for future technologies. So first, I'm just going to talk about quantum computing. So a classical computer basically works by encoding information in binary, so zeros and ones. It's just a different way of representing numbers. We represent numbers in base 10, but a computer thinks in terms of base 2. And this is what numbers look like in base 2, or 5 and 4. Now, a conventional computer, you have to encode this information into some physical degree of freedom inside the computer. And basically, computers are just massive switchboards or transistors, and each switch can be either off or on. And the off state sort of encodes a 0, and the on state encodes a 1. And suppose we want to do an addition, we add 4 and 5. So we're adding these two 3-bit numbers together. And yeah, we just add the way we're familiar with. So 1 plus 0 is 1, 0 plus 0 is 0, and 1 plus 1 is 2. But in 2, we have to carry, in binary, we have to carry the 1. So and then this is the binary representation of 9 as expected. So this is how a classical computer would add two 3-bit numbers. So instead of having switches, a quantum computer will encode the information into qubits. So what does a qubit look like? Well, we might have, for example, a particle which is vertical polarization might encode a 0, and a horizontal polarization might encode a 1. But we can also have superpositions, right? So we can prepare the qubits in a state that's sort of this combination of 0 and 1. And so what happens then if we have 3 qubits? Well, because of this huge explosion in the complexity, we can actually encode every single number every single 3-bit number, so 8 different numbers, 0 to 7, inside this system. So this 3-qubit system is in a superposition of every possible number between 0 and 7. So what happens then if we repeat our addition operation with these 3-qubit systems? Well, you can imagine these sort of 8-sided dice, which are labeled with every number between 0 and 7. So one operation for a classical computer would be like taking the number on one face of each dice and adding them together, and you get an answer. One operation for a quantum computer would give you this huge combined state, which encodes the entire distribution of all possible outcomes for the sum of these dice. So you roll these dice, and you can get anything between 0 and 14. And the resulting state encodes every single outcome, every single one of these individual calculations, and there's 64 separate calculations because you're adding two numbers which can each be from 0 to 8. And it's also weighted by the probability of getting this sum as well. So you can see how this one quantum operation is much more powerful than a classical operation, and that's great. It seems exponentially more powerful because this is just with three bits on each thing. As you scales it up, you get this explosion. But there is a catch, which is that you can measure this state, and when you measure it, you'll only get one outcome, right? So you can't actually extract all of the information from this state in a single cycle. So in general, if you wanted to determine this whole state, you'd have to repeat the process many, many times. And this actually destroys the speed up for the vast majority of instances. And this is a shame, because if this weren't the case, then quantum computers would provide an exponential speed up for every problem. But because of this, it's actually only a very, very specific subclass of problems where quantum computers provide advantages. But they do provide advantages. Sometimes we can be clever, and we basically be clever by measuring them in a different basis to the number basis. So this is a number basis, but we can try measuring them in a different basis, a basis that consists of superpositions of these. So I'm not going to go into exactly how this works, but I'll just give you an example for a problem that we do know where quantum computers provide a speed up. And this is like integer factorization. So we can have a number like 385 and decompose that into its prime factors. So 385 is 5 times 77, and 77 is 7 times 11. And these are prime numbers. They can't be reduced anymore. So the process of deconstructing any number into its prime factors, it turns out, is really difficult for a classical computer. It takes them very long. The longer this number is, the harder it gets. And when you start getting sort of 100 digits in your number, it would take our best computers basically the length of the age of the universe of runtime to decompose them in this way. But we know of a quantum algorithm that can solve this much more efficiently. This was devised in 1994, and it's been experimentally implemented. This is a paper from 2012 from just down the road in Bristol, actually, where they realized Shor's algorithm on a platonic quantum computer, and the number that they factorized was 21, which is not quite on the scale where classical computers have difficulty factorizing, but this was 12 years ago. There's been a huge amount of progress since then. We still don't have a quantum computer that can beat classical computers, but yeah, there has been a huge amount of progress, and this was an important proof of principle demonstration to show that we can actually build these things. But actually, the class of problems where quantum computers are probably most useful is actually simulating other quantum systems. And yeah, there's another good quote from Feynman here, which is, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical." And actually, there's lots of problems in quantum mechanics that have huge relevance for us in our everyday lives. So one is sort of proteins. Our bodies are mostly made of proteins. The COVID virus was covered in proteins that help get into our cells. There's huge significance to understanding how proteins work. And proteins are big, complicated systems with thousands of atoms in them. So characterizing them is difficult. They're big quantum mechanical systems, actually. And so with a classical computer, it would be very difficult to simulate. But with a quantum computer, you can access this sort of exponential scaling that would allow you to properly simulate the behavior of these things, which has obvious implications in pharmacology, drug development, that sort of thing. Another is like superconductors. So superconductors are materials that can carry electricity with zero resistance, and they're used in MRI machines. So you have coils of superconductor material here that generate the big magnetic fields. What we'd really like is a superconductor that works close enough to room temperature and can carry high enough currents that we can transmit electricity over very long distances. But we don't have one. And the reason is that superconductors are quantum materials. We don't really have a very good model for how they work. We can't simulate them very well with our classical computers. But a quantum computer would give us the muscle that we need in order to potentially develop these new classes of superconductors. And then, then we could live entirely off geothermal energy from Iceland or solar power from the Sahara, because we could get electricity from places where it's cheap and easy to generate it and just ship it as far as we want, because these materials have zero resistance. Another, if there are any chemists in the audience, is like fertilizer development, catalysis. Catalysis is a process that we don't really understand. So actually 5% of all global greenhouse emissions are just from the production of fertilizer for agricultural purposes, because the process that we have for doing this at the moment is extremely energy intensive. It involves taking air, compressing it until it becomes a liquid, heating it up to hundreds of degrees. He uses it and wastes a huge amount of energy. But certain plants have bacteria that live in their roots that do exactly the same thing at ambient temperature. And they have basically these complex enzymes that live in those bacteria that can basically do what we can only do with this hugely energy intensive process at room temperature. And we don't understand how, because the way that these proteins work is a quantum mechanical problem. We can't simulate it. What we'd like to be able to do is to be able to emulate it. But we need a quantum computer to be able to do that. So these are all potential applications where a quantum computer would be really useful. Another application is quantum cryptography. I'm running a bit short on time, so I'm gonna run through this quite quickly. But basically, if we have two people who want to send a message to each other, but they have a channel which may or may not have an eavesdropper in it. So yeah, we use Alice and Bob as the end parties, and we call the eavesdropper Eve. And they want to send a message, kill Eve, which obviously they don't want Eve to hear. And one way that they can basically protect this message from Eve is if they each have a string of random numbers, they can scramble this message by the same string of random numbers. And basically, if each of them knows this string of random numbers, but Eve doesn't, then they can send it. And Eve will have no idea what this is because she can't reverse the process because she doesn't know what these numbers are. But Bob will be able to reverse it. So the problem of communicating securely basically just boils down to the question of, can we distribute random numbers between Alice and Bob? And you also have to assume that any channel that they have for distributing these random numbers can also be intercepted by Eve. And there's a quantum mechanical protocol for doing this. So basically, Alice will send a bunch of randomly prepared photons. Bob will measure them in a random basis. He'll get a bunch of random outcomes. Then Alice will basically announce what basis she's encoded these in. So you can see these guys are encoded in the horizontal and vertical basis, whereas this one's encoded in the diagonal and anti-diagonal basis. Bob will hear Alice. It doesn't matter if Eve hears this. This is on a public channel, which means that yeah, Eve can listen. They basically, but Bob then discards any outcomes which are prepared and measured in a different basis. And then if Eve tries to measure, basically what this boils down to is because in quantum mechanics, the process of measurement actually has an effect on the state, and this is unavoidable. This is an intrinsic feature of quantum mechanics. So if Eve wants to intercept the information that's encoded in these, she has to perform a measurement. And the process of measurement can be basically, you can design this in such a way that this interference of Eve trying to measure will then actually create a bit flip, which will alert Bob and Alice to the fact that that someone's intercepting the message. So this provides a sort of fundamental form of encryption where basically you can certify that a message has been transmitted in a way that it's fundamentally impossible for anyone to have eavesdropped. And if someone is eavesdropping, then you can cancel the protocol because you know that your message isn't secure. Another application, so some of you will have seen this. This is a picture of a black hole that was taken by the Event Horizon telescope. And the way this worked is they had radio telescopes all around the world on opposite sides of the world. And they were looking at this black hole, getting radio signals from this black hole. And there's a way that you can basically interpret these messages to reconstruct this image. But it requires you to have timing resolution to within the period of this wave. And these are radio waves. So they have a period of about 1 picosecond, which is about a trillionth of a second. But these guys, to their credit, they managed to get these clocks on these different telescopes synchronized to within 1 picosecond. Now, what we'd like to be able to do is to do this at optical frequencies. So then we could build a very long baseline telescope the size of the world. And basically, the reason you want to do this is because the resolution that you get is kind of proportional or inversely proportional. Yeah, no, the resolution is proportional to the distance between these telescopes. So if we could do this, we'd basically have a telescope with an aperture the size of the Earth. And this would be enormously powerful. We'd be able to image planets around other stars and do all sorts of things. But the problem is that we need timing resolution to within the period of visible light, for example, which is 1,000 times shorter still, 1 femtosecond, which is a millionth of a billionth of a second. And this is really difficult. But it turns out that there's a way that you can achieve this if you're able to distribute quantum entanglement between different parts of the world. Yeah, this is the paper that introduced that concept. It's quite recent, as you can see, only 10 years old. So because of these applications, people are interested in building these quantum networks, and there's a plan underway to build a quantum network across the south of England that will allow entanglement distribution between different nodes. So now I'm just going to briefly go over sort of the optical photonic part of the talk. So the quantum theory of light sort of was approached from an opposite direction to electrons. Electrons were classically viewed as particles, but then we discovered that they had wave-like properties, whereas in the classical theory, light was a wave, but then because of the photoelectric effects and the ultraviolet catastrophe and the work of Planck and Einstein, it turned out that it was actually made of particles. And those particles are really, 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 really tiny. So how many particles are there in a laser beam? So I've got a laser pointer here, and some of you may have noticed I have a bar of dairy milk behind me. So the question is, this is the audience participation part of the talk. The question is, how many photons does this laser pointer emit every second? We can calculate this, and it's a very big number. So instead of the closest person to actually guessing the number, I'm going to give this to the person who guesses the closest to how many digits this number has. So if anyone gets it exactly right, then it's first come, first serve. But who wants to shout out a guess? So, huh? A billion digits. Okay, that would be a very big number. 45. Okay, 144. Leah, you should be able to guess this. My postdoc is in the audience. 42. One more guess. 350. Okay, well, you all guess way too high, which sort of like blows the wind out of the sails a bit. So the number of photons is 16 quintillion per second, which is 17 digits. So who said 42? You're actually closest. Yeah.
That feels like a way of thinking.
So it's a lot lower than you were guessing, but nonetheless, this is a really big number still, right? Now, it was very difficult to do experiments with quantum optics because these photons are so small. You know, there's 16 quintillion of them in a tiny laser beam. So being able to do experiments with individual photons is very difficult. And we didn't really have any way of doing it until the invention of the laser in the 1960s. Now, lasers basically emit, so if this is a pulse laser, they emit light with certain very specific properties. And if you were to count how many photons there are on each pulse, you get actually a different number of photons in each pulse. It's a statistical distribution. And this distribution is an intrinsic property of how lasers work. For those of you who know some statistics, it's actually a Poisson distribution. This is kind of suboptimal for some applications. Like, for example, suppose you have some medium and you want to know how absorptive it is. So you send in some light and you want to measure how much light basically comes out. If you don't know how many photons you're sending in, then how many photons you get out is not very useful. But we can prepare a kind of light called amplitude squeezed light, where there's a much smaller distribution. So here I've shown every pulse contains exactly 4 photons. And then in this case, it's much easier. You can say, okay, well, I know I was sending in 4, and then I detect 2, so I can estimate the transmissivity to be 50%. So you build up a much better estimate for how absorptive or transmissive this medium is using this. And actually, this has already found application. So it's a slightly different problem, but using these squeeze states, we can improve the sensitivity of interferometers. And this is the gravitational wave interferometer. There was a talk here at BRLSI a couple of months ago on gravitational wave mergers and using data from this experiment. And you can actually improve the sensitivity of this, which gives you more information about the waves emitted by merging black holes by injecting squeeze light. Yeah, because actually this is such an amazing piece of engineering. It's actually limited by this so-called shot noise, the statistical fluctuation in the number of photons in a laser beam. So we can also make sources of single photons. Basically, we can make a material where we can hit it with a laser beam, and some of the time, 1 photon in this laser beam will split into two photons, and those will separate out, and we can detect. So this pair emission process happens randomly, but sometimes we can detect this photon, and when we detect this photon and it clicks, because they're always generated in pairs, we know we have a photon here. And this process is called heralded single photon generation. And it's a probabilistic process for giving you 1 photon. It doesn't work all the time, but sometimes it will tell you that you have 1 photon. And when it tells you have 1 photon, you know you do have exactly 1 photon. And this is really useful. And more recently, we've developed these quantum dots as well, which are devices that are so-called push-button single photon sources. Basically, you sort of excite them with a laser pulse, and then they will give you a photon, in principle, up to 100% of the time. So these are single photon sources that we have. So what would a photonic quantum computer actually look like? Well, you might have a huge array of these photon sources, and you prepare each photon into a superposition state, and then you send them into a big interferometer like this. So this basically sort of crosses the paths of all these photons and interferes them. And this thing basically functions as a processor. So this is your sort of initialization, and this is a processor, and then at the end you do your detection, which is your readout. So this is basically the photonic quantum analog of a microchip. And in fact, people are trying to build these sorts of things on semiconductor chips. Well, yeah, chips just like conventional computers use microchips for their processors. In the final note, I'll just talk about what we're working on in Bath. So we work on fiber-based sources of quantum light. Basically, you have a similar process here where you generate these two photons statistically by sending in a bright laser beam. We have to design fiber with very specific properties at these wavelengths of light in order to make this process efficient. So that's one of the things that we're doing up at the university. Here's a microscope image of the precursor for one of these fibers that I made. And you can use these sort of things to do both heralded photon generation and squeeze state generation. So these are very useful sources technologically. Just about how we do the fabrication, we design our fiber, and then it's a bit like drawing Blackpool rock. So we literally just make a physical stack of fiber, and then we lower it into a furnace, and then we pull it, and then we get this microscopic structure that is just basically a sort of scaled down version of the thing that we've built, on a centimeter scale. So this is how we can make these tiny structures that we then use as quantum light sources. We also need ways of detecting these photons, and there's been huge advances recently in photon detection. So in the early days, people used photomultiplier tubes, which were slow and low efficiency. But now we have these superconducting nanowire detectors. We're just about to get a set of these at the university, very modern ones. So basically, I won't go into too much detail about how these work because I've already massively overrun. But yeah, these are really fancy and give you actually almost deterministic photon detection, which, considering, I'm making 16 quintillion of these things every second, to be able to deterministically detect one of them is quite a feat of engineering. I'll go over the key takeaways of the talk. So quantum mechanics is well established and consistent physics. So if there's one thing you take away from the talk, I just want you all to think, yeah, this is not this is not magic. Just keep a bit of a skeptical attitude towards some of the esotericism that surrounds quantum mechanics. There's a lot of people at the fringes who say lots of weird stuff. Particles can be in a superposition, but these are very fragile. Basically, doing anything with quantum mechanics involves isolating systems from their environment. Superpositions of multiple correlated particles we call entangles, and entanglement is a subtle property. It defies locality, but you can't use it to communicate. So, there's no way that we'll be able to defy the speed of light to transmit messages instantaneously using entangled particles. That's not how it works. Key takeaways for the second part of the talk. So all quantum technologies involve protecting these tiny systems from outside influences. This is really hard. This is why it's taken us 100 years since the discovery of quantum mechanics to get to the point where we can think about actually building a quantum computer and realizing these other applications. Quantum computers fundamentally are control clusters of entangled qubits. They're exponentially faster than conventional computers for some specific kinds of calculation and simulation. So quantum computers are never going to replace your smartphone. You're very unlikely to have them in your house. What they might replace is some of the tasks that we're currently and inefficiently using supercomputers to do. And they'll be able to solve certain, quite specific, but nonetheless very important problems. But you're unlikely to have one at a domestic scale. They're complementary to classical computers. They're not going to replace them. Quantum encryption makes silent eavesdropping impossible, and there's other applications like long baseline telescope sensing, and fiber optics is a great way to make this happen. Yeah, so that concludes my talk. I'm sorry I've overrun a bit. I'll just leave you with this great picture. So this was one of the few occasions where real life actually kind of emulates the movies, and all the main characters actually did physically get together in one place and just sort of bash it out. This was a conference in Solvay in Belgium in 1927, where the principles of quantum mechanics were laid out. And some of the people that I've highlighted, I've mentioned that they were all here. So Max Planck, Einstein, Schrödinger, and Heisenberg, I've mentioned. Also Marie Curie, you'll probably know, and you might have heard of Paul Dirac as well. So all of these guys, they gathered together in the same place, and they worked it out. It must have been an amazing place to be. Yeah, so again, sorry for overrunning. That's the end of the talk. I hope you learned something. Thank you very much.
Oh, we have some time for some questions. Bearing in mind that there are people who are not in the room who would like to hear a question, if you have a question, please could you put up your hand? And I'll bring the microphone to you.
This is the part I was most.
Anyway, it's a very fascinating talk, but my question is slightly tangential to the main part of your course talk. But at the beginning, you said the difference between classical mechanics and quantum mechanics is classical mechanics is deterministic, quantum mechanics is not. But what about chaotic systems in classical mechanics, which is probably most of the real world examples? How do they map to the quantum equivalence? You know, take 3-body, 4-body, 5-body, multi-body problems, which can be very chaotic in classical mechanics. What happens when they're sort of in the quantum world?
Yeah, that's a really good question. So the thing is that within classical physics, chaotic systems are actually in principle still deterministic. What chaos theory basically says is that the precision that you need to know the initial conditions for a chaotic system in order to predict the outcome basically gets exponentially sort of smaller depending how far you want to predict the future. So if you take the weather, for example, the classic chaotic system, basically every further day you want to know the weather in advance, you need exponentially more precise information about the state of the weather today. But it is still deterministic in the sense that if you knew exactly what the state of the weather is today, you could predict it infinitely far in advance. Yeah, within classical mechanics, chaotic systems are still deterministic. And you're right that practically it doesn't. Practically, we might as well imagine chaotic systems as being probabilistic, because beyond a certain point, there's no way that we can know the initial conditions well enough. But there's an important sort of fundamental distinction, which is that they are still in principle deterministic.
Hello. You started in the first section by describing quantum as a wave, but in the second you moved on to explain it as a particle. Do you have a comment on which one it is?
Well, it's both, isn't it? Yeah, I mean, so actually, one of the reasons that you could think of the classical theory of light as being wave-like, whereas the classical theory of electrons is particle-like, is an interesting consideration. So photons basically do not interact with the environment very, very keenly. Unless a photon is absorbed, in fact, they rarely interact with the environment. And there are certain processes like reflection and refraction where the photon will pass through a medium and survive. But these processes are coherent, and that means that the environment doesn't effectively realize a measurement on them. So although they do impact the photon, they don't effectively measure it. So for that reason, the wave-like behavior of the photon seems to kind of dominate. And when we were working out classical physics, it seemed like it seemed like photons behave like waves. And in fact, in the case of photons, it's the particle-like behavior that was very difficult to spot. Whereas with electrons, it was the wave-like behavior that was difficult to spot. It's a bit of a historical coincidence, actually, that the two kind of were identified at the same time. But to answer your question, all quantum effects, all quantum phenomena are both, basically.
Thanks, Joe. You mentioned that quantum computers need to be cooled to very low temperatures in order to be able to work. And yet we know there are many quantum effects actually apparent and working at much higher temperatures. And I wondered if you had any comments on the distinction between the requirement for very low temperatures and very quiet systems and the actuality of quantum processes working at higher temperatures.
Yeah, that's a great question. So in terms of what temperature we need to operate a quantum computer at, it actually depends on how we would realize it. So there's actually, I talked about photonic quantum computers here, but there's lots of different ways that people are trying to build quantum computers. And some of them use superconducting qubits. And for those kinds of computers, yes, you do need to cool it down very, very, very much, because if it's warm, then you'll basically get qubits being randomly scrambled by thermal effects. Actually, the processing aspect of a photonic quantum computer can work at room temperature, because photons at visible wavelengths or near visible wavelengths, which are the kind of wavelengths that we normally work at, have much higher energies than the energies at which you get spontaneous emission of photons at room temperature. So actually, the processing part of a photonic quantum computer can operate, at ambient temperature. The difficulty is actually the detection stage. So it's the detection of single photons where currently the methods that we use to detect them require cooling. So yeah, it's not really a fundamental aspect of how quantum computers work. You have to cool them. It depends on the hardware implementation.
You'll have to repeat on it. I think that the answer is very interesting, I think, because it has implications for quantum effects in life, the processes of life, where it is apparent that they work in that way. And that's because of the photon nature of the interactions.
Yeah,
I think that's a very interesting conclusion. Thank you.
Yeah, so in general, optical frequency excitations, like, for example, you would get in photosynthesis, where a chlorophyll molecule in a plant absorbs a visible wavelength photon, and then you get an excitation inside the molecule which has comparable energy to the visible photon. Yeah, these kinds of processes are kind of robust to thermal effects at ambient temperature.
Hi, you showed a dilution refrigerator for the detection system.
Yeah.
If you need a dilution refrigerator to detect for the photon quantum computer, what advantage do you get over an electron quantum computer with the supercooled qubits?
Yeah, so there is kind of a difference in the scale at which you have to cool. Basically, because one of the reasons you're cooling for electronic quantum computing is that you get thermal excitations that basically cause the qubits to flip. Because the characteristic energy scales of these qubits are so much lower than photonic excitations, yeah, basically you need to get it very, very cool. And in fact, even if you cool down to like millikelvin, this is still one of the dominant sources of noise for these devices. Whereas to do superconducting nanowire photon detection, these devices typically operate at sort of like 4 degrees Kelvin, so 4 degrees above absolute zero. So many orders of magnitude higher than the kind of scale you need to get to eliminate noise in.
So my problem was that I recognized the dilution refrigerator when you put up your detection system.
Yes.
A very simple question. Do quantum physicists working on mechanical devices pay much attention to what's happening in biological systems? Because obviously you've got quantum effects happening there at very low temperatures, otherwise we'll all explode. So how's that working that could be simulated into a more mechanical process?
Yeah, well, it sounds like you need to have a conversation with the gentlemen to your left who are working on exactly this sort of thing. But yeah, so there is this field of quantum biology, which is basically studying the extent to which these quantum effects play a sort of a qualitatively important role in biological systems. And it's I think would still be considered quite a nascent field, but there are nonetheless lots of examples where we know that quantum effects, this wave-like behavior is really important. So it seems to be really important in explaining why photosynthesis is so efficient. I also gave the example of nitrogen sequestering bacteria in plants. The evolution of these things is basically evolution solving a quantum mechanical problem for us by trial and error. There's other examples, like apparently how pigeons navigate, I think, and how smell works. These are all examples where it seems that quantum mechanical effects play a qualitatively important role in how things behave, how biological systems behave. There's a big controversy about what role quantum mechanics might play with regards to consciousness. But that's a completely different topic. Well, it's relevant, but it's probably beyond the scope of this talk.
I might just add that we had a question come in from someone who has been attending the lecture remotely, which is very much a cognate question to the ones that we've been discussing over the last few questions here. And basically what the questioner, the remote questioner, asked was, is it actually necessary for a quantum of energy, say a photon, to interact with something and yield some of its energy to be in order to interact and thereby collapse its waveform. Is that how the waveform collapse occurs? That energy is being bled off, or do we really have literally no idea about the nature of the interaction that's required to collapse the waveform?
So there's sort of two parts of that question. One is, does there need to be some transfer of energy? The answer to that is no. So you can do measurements on a quantum. They're so-called non-destructive measurements. Actually, the lab I was in Paris, one of the guys working there was a guy called Serge Haroche, who won the Nobel Prize for non-demolition or non-destructive measurements of photons. So this was a procedure where you could basically perform a measurement on a photon, like determine its polarization, for example, but still have the photon afterwards. So most of the all the measurements I've talked about here, at least in the case of photons, involve sending it into a detector, and that absorbs and destroys the photon. But there are ways of doing it that don't involve an exchange of energy. Perhaps the other part of your question, was what is the mechanism by which wave function collapse happens? That question is what is sometimes called the measurement problem, and it's without doubt the subject of the largest amount of philosophical literature and debate in the whole of physics. Some people would say that there doesn't need to be any mechanism in a sense, but then there are interpretations of quantum mechanics where the measurement does sort of actually physically collapse the, well, yeah, it's basically something happens to that destroys the wave function. It's a whole thing. Yeah.
Another way of putting that question, I know we're struggling a bit here, is that there's a really quite a well-developed body of information science that says that information is formally equivalent to energy.
Yes.
And so if you derive some information about the state of your quantum, surely energy must be involved somewhere.
Yeah. It definitely is. So in the sense in which energy is kind of equivalent to information is that energy basically tells you the rate at which you're exchanging information between different quantum systems. So like a high energy excitation basically involves like, you know, like a very ultraviolet photon, for example, is exchanging information very fast between, you know, two different quantum systems. Now the non-demolition measurement, I suppose, it doesn't involve an absorption of energy in the sense that you can have horizontal and vertical polarization that have actually the same total energy, but in a sense that energy is kind of distributed in different states. So energy is involved in a sense, but not necessarily in extracting energy from the quantum system, possibly just sort of swapping information around different places within the quantum system. Sorry, that was a bit hand wavy, but yeah, it's.
I think we're all going to have to think about
Yeah,
that. I think time's moving on. We're almost at 9 o'clock. So I'm going to draw tonight's proceedings to a close. I don't know about you, but I thought that the explication of what's going on here was just outstanding. Very, very clear. Thank you so much, Alex, for that. If you leave us a lot to think about at the end, well, it probably means you'll have a job for quite some time.
Thank you. That's a very positive spin on it.
Thank you so much.